Okay, hello everybody. Today we will be doing section 4.6, and it covers the mean value theorem, or at least that's what it's called. Actually, in this section we'll be covering more than one theorem, and if you guys remember, a theorem is just something that says if you meet these conditions, then something is true. So we're just going to cover them really quick, and it should honestly be a fairly quick section just because there's not too much information. Okay, so the first theorem is Rolle's theorem. And this says, so these are the conditions we need to have. Let a function f be continuous on some closed interval a to b, represented by the square brackets, and differentiable, aka you can take a derivative, on the open interval a to b, so not including the endpoints because an endpoint derivative isn't super defined. And the second condition is let f of a equal f of b, which is basically saying let the y values of the endpoints be equal. Then, so this is the result. So we have our conditions and then our result. There must exist at least one point, say x equals c, in the interval a to b, such that f prime of c is equal to 0. Okay, so this might seem a little complicated just from the statement. This I would consider it a cheat sheet information just because it's a named theorem, so you know it's at least a little important. And let's draw some examples. So if I have a graph, and this is f of x, graphing against x, and we're saying it's continuous on some interval a to b, so we're going from a to b, and we're saying that the value of f of x at a needs to be the same as the value of f of x at b. And we could do whatever we want in the middle here. Okay? And if you look, this guy has actually several points where the value of f prime is equal to 0. So f prime equal to 0 just means that the slope of the tangent line is flat, or is equal to 0. So like here, 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 which you guys know means that there's either a maximum or a minimum, like a local maximum or a local minimum on these points. Okay? Just for like another example, these are just examples. You can graph f of x over here. We have a and we have b, and we know we want a and b to be the same. We could also just have a constant line in here, and then f prime of x equals 0 for all values x in the interval a to b, right? Because we have a 0 slope for this entire line. Whereas over here, we have a bunch of different 0 slopes here, 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 and here. And so those are all examples of that c value. So this would be like c sub 1, c sub 2. These are just places where c sub 3, c sub 4, our slope is 0, etc. But note, it just says there has to be at least one. So we know somewhere it has to be. It doesn't have to be more than once, though. So if this were just like a single parabola, there'd be a slope of 0 at the maximum. Okay? So it's just important that you make sure if you're using this theorem that the function is continuous and differentiable. So we talked about that before the last exam. If you look at the exam review, there's some examples of that where we discussed it. So that should get you guys through that. Let's see here. All right, so now we're going to move on to the main theorem of this chapter, or this section, which is the mean value theorem. And this one will actually have an example because it's more, I guess, example applicable. So the mean value theorem, the conditions, so the stuff that has to be true in order for this to work, is that f is continuous. So it's pretty much the same starting off as Rolle's theorem. F is continuous on the closed interval a to b. So that's just like Rolle's theorem. And differentiable, aka able to take the derivative on a to b, open this time, just like Rolle's theorem. Then, these are our results. There exists at least one point. So again, this is very similar to Rolle's theorem. X equals C in A to B, but now here's where it gets different, such that f of B minus f of A over B minus A is equal to f prime of C. So basically, you guys know that this is the average slope, or the slope of the secant line. On the interval a to b. And we know that this is the instantaneous slope. Or slope of the tangent line. On a to b. Or sorry, not on a to b. At x equals c. Okay, so this theorem is just saying if you have a continuous function that is differentiable, then for at least one time, the slope, the average slope, is equal to the instantaneous slope. So let's draw a picture. So if we have f of x and x, and we want a function that's just continuous from a to b, so these don't have to be equal this time, it can be anywhere. Then if I have this, for example, my secant line from a to b is not like that. That was not drawn well. There we go. That's better. So this is the secant line. And it's saying that at some point, let me see how I can draw this better. Okay, at some point, this ends up being a tangent line. So this is just to help me draw my picture better. I'm trying to draw lines parallel. Nope. Hey, Kenzie. Sorry, guys, my family is being obnoxious. Okay, anyway. So I guess my secant line would look, or sorry, not my secant line, my tangent line would look something like this guy. Wow. Turns out I'm not as good at drawing on this as I thought I was. Okay, so that would be like what my tangent line would look like. We can erase these guys. Imagine, for the sake of this example, that this is touching right here, so that's actually the tangent line. So we have this as the tangent line. And at this point, which this theorem calls C, that tangent line and that secant line have equal slopes. Okay, so let's do an example really quickly. Also, the mean value theorem is cheat sheet information because you know that a named theorem is probably pretty important. So, example. Oops, I want this to be black. Whoops. Determine whether f of x equaling 2x cubed minus 3x plus 1 satisfies the conditions of the mean value theorem, which we'll call MVT, just to make it shorter, on the interval -2 to 2, and then if yes, find those values C. So find all those points where our tangent line has the same slope as our secant line. Okay, so first of all, the first question was, does it meet conditions? And first of all, we need to check and see if it is continuous everywhere. On our interval, so from -2 to 2. And the answer is yes, because it's a polynomial and polynomials are continuous everywhere. And then our second one is it differentiable on -2 to 2? And that is again yes, because polynomials are differentiable everywhere. And we talked about differentiability and continuity again at the beginning of this past exams review and also at the beginning of the year. So hopefully you guys are relatively familiar with those. Okay, so for part 1, the answer is yes, the conditions are met. Okay, so then part 2 is we want to find the C values, C in quotes because it's just the C it talks about in the theorem, which is the points at which our tangent line is equal to the slope, our tangent line slope is equal to the slope of our secant line. So first to do this, we're going to find, here I'll write it in steps again. So step 1, find the slope of the secant line. Which we know is f of b minus f of a over b minus a, which in this case, b is equal to 2 and a is equal to -2 because we're moving on the interval from -2 to 2. So a is our first value, b is our second value. So we want f of 2 minus f of -2, oops, -2 over 2 minus -2, okay? And when we plug this into our original function is up here, we have 2 times 2 cubed minus 3 times 2 plus 1 for our f of 2. And then we have to subtract all of f of negative 2. So we want to make sure we have this parentheses here, so we remember to distribute this negative sign. So we're going to plug in 2 times negative 2 to the third minus 2 times negative 2 plus 1. And that's all over 2 minus negative 2, which is 4. Okay, so we get 2 times 2 cubed is 8 times 2, which is 16, minus 6 plus 1, minus, in our parentheses, we have 2 times a negative 2 cubed, which is 2 times negative 8, so that's a negative 16, minus 2 times a negative 2, which is plus a positive 4, and plus 1. So when we distribute this, sorry, this is all over 4. When we distribute this, we have 11 minus a negative 9 all over 4, which ends up being equal to 20 over 4, which is 5. Okay, so now that we have that, we're going to eventually use that to set it equal to our tangent line and figure out where that tangent line is equal to 5. But first we need to just find the general tangent line, or the derivative of f of x. So we have f prime of x is equal to, here I'll write x again, or f of x again, so we have it right there, 2x cubed minus 3x plus 1. So f prime of x is equal to 6x squared minus 3. Step 3 is to set step 1 and step 2 equal to each other and solve for x. So we're trying to look for where 6x squared minus 3 is equal to 5. And that gives us where 6x squared is equal to 8. So if we divide this out, we get x squared is equal to 4 over 3. So c is equal to plus or minus the square root of 4 over 3. Right? Because when we take a square root of our x value, we get a plus or minus over here. Okay? So basically what this is saying is f prime of c equals 5 at c equals plus or minus the square root of 4 over 3. All right, so that would be your answer. All right, there are 2 things I want to talk about, and then we're done. So first of all, these are just some like side notes. About derivatives equaling 0. Okay, so first of all is if f is differentiable, which should be normal to think about because you can't say something about a derivative if you can't take the derivative, so that makes a lot of sense. And f prime of x equals 0 for all points on some interval a to b. I guess we would want to include a and b. Then f of x is constant on a to b. Basically, f of x is a flat line. Right? Because if we have f of x as a flat line, and I were to draw in the tangent lines, which is just the instantaneous slope at any given point, they're equal to each other because the slope is constant. Well, I guess it's not f of x equals f prime of x, but f prime of x is equal to 0 because the slope of the tangent line is equal to 0. So f prime of x is equal to 0. Okay, and then the second point is also about zero slopes. So well, it's more about two functions that are equal to each other. So I guess their difference is 0. So if f and g are differentiable, so you can take the derivative, and f prime of x equals g prime of x on an interval a to b. Oops. Actually, guys, up here, I do want to change this to an empty interval because we can't really talk about the derivative at an endpoint, which I talked about before. So, but it still does mean that it's constant on a to b, inclusive. So square brackets are appropriate. Down here, you just can't take a derivative at an endpoint. Okay. Anyway, so if f and g are differentiable and f prime of x is equal to g prime of x on an interval a to b, then f and g differ by only a constant, which is another way to say that they're essentially parallel. It's like a loose version. I'm going to call it curvy parallel. Or not parallel. Yeah. I'm thinking of perpendicular. Guys, my R's look just like my V's. Curvy parallel. Not a real word. Also not spelled correctly, I don't think. I think there's one R. Parallel. Okay. And that would look like this. So if I have some function f of x, and I have some function, ooh, you know what? I'm going to get fancy with this. I'm going to make it identical. Okay, so this is f of x. We're going to call this g of x. We can see that these are what I'm calling, in quotes, curvy parallel because the distance between our functions stays constant the whole time. And basically what's happening here is if we look at our slopes of our tangent line, so let's draw these ones in orange. I would have a slope of the tangent line there. I could draw a slope of the tangent line there. I could draw a slope of a tangent line here, slope of a tangent line here, slope of a tangent line here, slope of a tangent line here. Let's see, slope of a tangent line here. That was a bad tangent line. Slope of a tangent line here. We can see that when our values of x are equal, our different slopes of the tangent lines are equal. Right? So the slope of f of x here is equal to the slope of g of x. The slope of g of x here is equal to the slope of f of x. That's what this statement is saying, is if our derivatives are equal to each other on this whole interval, then f and g differ only by a constant, which is to say, if we look over here, this difference right here, let's call it c, our constant, then that difference stays the same for our whole drawing. So it's always a difference of c. Right? So over here too, this is equal to c. And basically what that means is that f of x is equal to g of x plus c, or g of x is equal to f of x minus c. So that's what it means by differing only by a constant. Alright guys, so that's pretty much it for what we're covering today. It was just a lot of theorems. Yeah, so that's 4.6. I'll see you guys for 4.7 on Friday.